Alright, so we're looking at, in this section, logarithmic equations. So I start off by showing you, or asking you to find the inverse of this exponential function. So when you try and find the inverse of this, you do the same steps. You change y equals, and then you switch the x's and y's. But then the question is, this is a y. How do I solve for y? So instinctively I want to do like the root of y, but I don't know what y is. So what we bring in now are logarithmic functions, and a logarithmic function is the inverse of an exponential function, and that's important to keep in mind. So x has to be greater than 0 and b has to be greater than 1, just like with an exponential function. And so log base b x is equivalent to b to the y equals x, which is what we're trying to do up here. So rewriting each of these, so the base is 2, the base is 3, the base is e, the base is b. So in this case we're basically rewriting this as the base raised to the exponent. So 2 raised to the third power is 8. In this one the base is 3. 4 is the exponent, so 3 raised to the fourth power is 81. E raised to the fourth power is x. So I could actually put that in my calculator and figure out what x equals, right? B raised to the third power equals b raised to the third power. That seems a little bit obvious, but that is truly what's happening there. Okay, and then the same token, I can take these exponential problems and rewrite them as logarithmic. So with the log, this is always your base. So our base is 5. The 625 is your result, and the 4 is your answer. So technically, we don't have the ability to put that in our calculator. So on our calculators, our graphing calculators, we have a log button here on the left, but that's log base 10. So we can't put that in our calculator and get the answer. There is a function, I forget where it is, I'd have to find it, where you can find the value of the log, and I'll find that and show it to you someday, but it's not important. Here I can do log base 3, here's my exponent, and here's my result. So 3 raised to the second power equals 9. Here it's going to be log base 8. Base A raised to the b power is equal to c. Okay, so another thing, if we talk about this again, we said that these two are inverses of each other. So remember when we talked about composition of functions in section 1, we said that if I take this and substitute it in here, then that means that it should equal x, because with compositions of functions, they should equal x. So if I take f and g, and I say they're inverses, if I take g and substitute it into f, then that should equal x. Or if I take f and I substitute it into g, then I should have x. So what I'm doing here is I'm taking the exponential function, and I'm going to substitute it in here for x. Right? And I'm going to take, and I end up with a problem that looks like this. Okay? So when I take the f and I plug it into g, I end up with this problem. And because these are inverses, I know they should equal x. And the same thing here, I'm going to take the logarithmic and I'm going to substitute it in here. This one looks very strange, and I'm going to end up with x. Okay, so let's look at a couple examples of just that, and then we'll talk about the properties. So if I have log 6 to the x power equals 3. So basically I'm saying 6 to the third power equals 6 to what power? So x has to equal 3 to make those match up. This one is definitely not as obvious, so we look for matches. Our base here is 6, our base here is 6. So both of our bases are 6. So the missing part should be 4. So this should be 4. Okay, some more examples of that. Let's look at these. So if I have 8 log 8. So again, 8, those are my bases. So the missing part is 4. In this part, these are supposed to be my bases, right? So x should equal 7. On this one, okay, so my bases are the same, so the missing part is 3. On this one, I'm looking for what x has to equal, right? So the exponents are both my 4s, and these are supposed to be my bases. So x has to equal 9. On this one, my bases are 7, my exponent is 5. My bases are 10, my exponents are 3, so x has to equal 3. Alright, so those are just some examples of how that works. Alright, so here are some properties of logs that we're going to be using today, and we're going to lead into the next, it leads us into solving equations with exponents, or with logs. So this one sort of makes sense. You can use your rule of conversions up here. So b raised to the first power equals b. That makes sense, right? B to the first power. Anything to the first power, it doesn't change. So that one's easy to justify. B to the 0 power, right? Anything to the 0 power is 1. So that one makes sense. This one's not too hard to understand. B to the x power equals b to the x power. That one makes sense. This is also one of them that we just did up above with the composition. Okay? So this is the one that's hard for people to understand. So when you look at this one, you have to keep in mind the composition problem. So our bases are the same, so my exponents have to be the same. So that's because of that composition of functions that we just talked about. So this is the property that you have to keep in mind to use, but that's the hardest one to completely grasp. Okay, so here's some examples. So if I want you to fill in the blanks, so basically this is saying 2 to what power equals 1. So x would have to be equal to 0. This is saying 8 to what power equals 8. So x has to equal 1. This is using that composition of functions. Again, our 5s are the same, so our exponents have to be the same. So our missing piece is 9. And this one, again, we can justify with exponents. 3 to the x power equals 3 to the 5th power, so x has to equal 5. Okay? Alright, so that's sort of like what we were talking about on the back. So when we're graphing logarithmic functions, remember that they're inverses of the exponential function. So in our exponential function, we're going to go through the point 0, 1 for this particular one, and 1, 2. So 0, 1, and 1, 2, there's my exponential function. So if I want to graph the logarithmic function that is equivalent to that, or the inverse of that, I'm going to switch my ordered pairs. And I'm going to graph 0, 1, and I'm going to graph 2, 1. And there's my exponential function. So now my asymptote has changed to x equals 0. So my asymptote was y equals 0. Now it's x equals 0. Notice that it is an increasing function still, right? But notice that it is in quadrant 1 and quadrant 4, whereas the first function, the exponential, is in quadrant 1 and quadrant 2. And that's true for all exponential functions. So sometimes the easiest way to graph your logarithmic functions is to think of them as exponential functions. So if I want to graph this logarithmic function, my base is 3, so I would think of it as 3 to the x power equals y. That's the exponential function. So for 3 to the x power, I have 0, 1, and 1, 3. So that means for my logarithmic function, I'm going to have 3, 1, and 1, 0. So 3, 1, and 1, 0, there's my logarithmic function. Okay, same thing here. 2 to the 3rd power, 2 thirds to the x power equals y. So I have the two ordered pairs 0, 1 and 1, 2 thirds. And so my inverse function, which is the log, would be 2 thirds 1 and 1, 0. So 1, 0 oh, here it is, 1, 0, and 2/3 1. So this purple line is my logarithmic function, and the red line is my inverse function, which is the exponential. Notice that line of symmetry, y equals x, is going right through there. So again, the logarithmic function covers quadrant 1 and quadrant 4, and it is decreasing, just like the original function was decreasing. Okay? So my translations, if I'm translating, I'm going to do the same thing that I did before. So my base is 6, so that means my original function is going to be 0, 1, 0, 1, and 1b, right? So that means my exponential function is going to be b1 and 1, 0. So this problem is going to add 1 to y and add 1 to x. So if I add 1 to y on this problem and I add 4 to x, that means I'm going to have 5, 1, add 4 to that, add 1 to that, and I get 10, 2. So that tells me what my exponential function is going to look like. I'm sorry, my logarithmic function is going to look like. On this one, again, 1, 0, and 6, 1, I'm going down 2, so I subtract 2 from y. So I would have 1, negative 2, and I would have 6, negative 1. Okay, and then I could graph those 2 points and get my logarithmic functions. Alright, so now we're going to talk about domain, and I think what I'll do is we're going to start another video and then we'll finish up domain in that.